All right, in this video, we are going to look at solving Ka and Kb problems. Now, solving these types of problems is going to be no different than solving any sort of K problem. So everything that we talked about in chapter 17 still applies for chapter 18. It's just that when we have Ka, that means a very certain thing. So again, note, Ka specifically means the acid, aqueous, plus water, liquid, forms the conjugate base, aqueous, plus H3O plus aqueous. Kb specifically means our base, aqueous, plus water, liquid, forms Hb plus, aqueous, so the conjugate acid form, plus OH minus, aqueous. Okay, so that's the first thing to remember. Okay, if it's always with water, right? So don't forget about the water. Okay, water is required for these. Actually, let me use the light blue for a watery color there. And so then don't forget, a Ka is an acid with water to form H3O plus, and a Kb is a base with water to form OH minus. And remember that they form their conjugates as the other product. Okay? Now, the other wrinkle in this is note, if we talk about pH or pOH, we need the equilibrium concentration of H3O plus to calculate pH and the equilibrium concentration of OH minus to calculate pOH. Lastly, we are going to assume that the initial concentration of H3O plus, so I, or the initial concentration of OH minus, depending upon the problem, is 0. In reality, it's actually 1.0 times 10 to the negative 7th moles per liter. But we're going to find that adding that number into your ICE table to solve these style problems is just going to make your work harder without actually adding anything to your final answer. Your final answer will be no different than if you make the assumption that basically we're going to solve for the equilibrium of the reaction with water and presume that autoionization has not yet occurred. Okay? So let's look at an example problem. We'll look at a couple. Okay, so let's say we have something like something called propanoic acid. So let's say we tell you that propanoic acid, which we're going to shorthand HPR, has a Ka of 1.3 times 10 to the negative 5th. Okay, and what we want to know is what is the pH of a 0.10 molar solution, aqueous solution, of HPR. Okay, what is the pH of this? So first, we got to write out our reaction. So HPR, aqueous. Now, this is an acid. We were given a Ka. It's written like an acid. So if this is an acid, then we are doing a Ka problem. And remember, Ka is acid plus water forms conjugate base, which would be Pr minus in this case, plus H3O plus. Okay, so ICE. Note, we're going to ignore water because it's a liquid and we're not going to include it in our calculation. And so note, our equilibrium expression is going to be our concentration of PR minus at equilibrium times our concentration of H3O plus at equilibrium divided by our concentration of HPR at equilibrium. To calculate the pH for this, we're going to need to take the negative log of the equilibrium concentration of H3O plus. Okay, so this is how we're ultimately going to solve it, but we have to do an ice table to do this. So our initial concentration of HPR is 0.10 molar, and then our initial concentrations of H3O plus and PR minus are 0. Now, PR minus is easy to assume is a 0. We just assume that HPR, so we assume no equilibrium yet. We also assume no auto ionization for water. So that's why we're assuming that the H3O plus concentration is 0 moles per liter, because we are assuming that water has not auto ionized. So in Raleigh, it has, but from a mathematical standpoint, it's not going to negatively affect anything to make that assumption. So if we calculate Q in this case, we get 0 times 0 divided by a non-zero value, which is just 0. And so Q is 0, which is less than K, 1.3 times 10 to the negative fifth. So that means our reactants are minus coefficient X, and our coefficients are all 1, and our products are positive or plus coefficient X. So our equilibrium concentration of HPR is 0.10 minus X, our equilibrium concentration of PR minus is X, and our equilibrium concentration of H3O plus is X. Okay? And so we would end up with X times X all over 0.10 minus X, and that is equal to our Ka value of 1.3 times 10 to the negative fifth. Now you saw, and note, by the way, that X is the equilibrium concentration of H3O plus. So that's what we're solving for. Once we know X, then we know the H3O plus concentration at equilibrium, which we can then plug into our pH equation to get what the pH should be. And note, since this isn't, we'll see that this is going to be an acidic pH. Okay, so we could do our little test here to simplify things and make our lives a little bit easier. So we'll do our test. We take our smallest non-zero initial concentration divided by our K value, which is 1.3 times 10 to the negative fifth. And that ends up being, let me get out my calculator here. So 0.1 divided by 1.3 exponent negative 5. And we find that that is 7,000. That is equal to 7,692, which is greater than 400. So X plus additions and subtractions of X can be ignored. So we'll rewrite this as X squared over 0.10 equals 1.3 times 10 to the negative fifth. So now it becomes fairly trivial to solve it. Remember, X is going to be our H3O plus concentration at equilibrium. Okay, so we take our 1.3 exponent negative 5, we multiply by 0.10, and then we take the square root of that, and we get a value to 2 sig figs. I'm not going to round it yet, though. 1.1402 times 10 to the negative third moles per liter, but it's going to have 2 sig figs because we have 2 sig figs here in our K value. If we take the negative log of that, I'll just keep it in my calculator and do it that way, I get a pH value of 2.94. As our pH. And that's it. That's all there is to solving these types of K problems. Okay, let's do another example where it gets a little bit trickier. Okay, so let's do another example. Now, let's say you're given a solution of sodium acetate, which has the formula. We'll just put NaC2H3O2, but we'll just write it as NaAC. So you're given sodium acetate in a 0.25 molar aqueous solution. Okay. You're also given that the Ka of acetic acid, which we can write as HAC, is 1.8 times 10 to the negative fifth at 25 degrees Celsius. We want to know what is the pH of this salt solution. Now, the moment you see Ka, you're going to think, oh, well, I need to solve a Ka problem to solve this. However, that is not what we have, okay? We were given this solution, and note that this dissolves to form sodium ions, which do nothing and we can ignore, and then C2H3O2 minus ions, which are bases. So this is actually a Kb problem, not a Ka problem. You need to pay attention, right? So if this is a Kb problem, so our base, I'm just going to call this AC minus. So if our base is AC minus, aqueous, plus water, liquid, in equilibrium, we get HAC. Again, we're just using that for shorthand for acetic acid. Okay. And then note, since this is acting as a base, we get OH minus as our product. Now note, we were asked to calculate the pH of this salt solution, but that requires knowing the H3O plus concentration. Okay, so to solve this one, we're going to be solving a Kb expression. Okay, conjugate acid at concentration equilibrium, OH minus concentration at equilibrium, all over the initial concentration of our base, which is that AC minus, the acetate ion, and then at equilibrium. Okay. So first of all, we need to know what Kb is to do this problem, and our OH minus concentration will help us find POH, but that's not what our problem asked for. It asked for the pH, which, if you'll remember, pH plus POH for a conjugate acid-base pair, well, pH plus POH, and so I'll write this up here. You just kind of need to memorize this. pH plus POH equals 14.00, 2 decimal places, at 25 degrees Celsius, which we're at. So to calculate pH, I could just take 14.00 minus my POH, and then there will be our answer. Okay, so there's a couple of tricky things in this. We need to figure out the Kb, which will let us find the equilibrium concentration of OH minus, that we'll then use to find the POH, which we will then use to find the pH. Okay, so a couple more steps in this case that make it a bit more difficult. Okay, now, how are we going to get Kb? Well, there's another thing we can remember. Remember, for a conjugate acid-base pair, so here's HAC, that's the acid form, and AC minus is the base form. There's our acid, there's our base, right? Ka of the acid times Kb for the conjugate base will equal Kw, which is 1.0 times 10 to the negative 14th. So if we want to know Kb, we just need to take 1.0 times 10 to the negative 14th divided by whatever our Ka value is, which in this case is 1.8 times 10 to the negative fifth. And that would give us 1 exponent negative 14 divided by 1.8, exponent negative 5, and we get 5.6 times 10 to the negative 10th. So we've got our KB now. We also know how to get our pH from our pOH. So now we can do the KB ice table problem. So again, our water isn't contributing anything. Okay, our initial concentration is right here. That's our 0.25 molar, because for every 1 mole of sodium acetate that dissolves, it will form 1 mole of sodium ions and 1 mole of acetate ions. Therefore, the concentration of the formula units is the same as the concentration of each independent ion. And again, we're going to assume 0 and 0, like we've done previously. Q equals 0. The moment any of your products are 0, Q equals 0. And of course, we know Q is less than K. So minus X plus X plus X. So at equilibrium, we get 0.25 minus X, and then X and X. And so setting this up, we would end up with X times X over 0.25 minus X, which is equal to our KB, which we calculated to be 5.6 times 10 to the negative 10th. Again, we could do our test. Okay, you know it by now. You take our smallest initial non-zero concentration divided by our K value, which is 5.6 times 10 to the negative 10th. And that is going to be a very, very, very large number. 0.25 divided by 5.6 exponent negative 10 gives us a very large value. 1, 2, 3, 4, 5, 6, 7, 8. So it's about 4 times 10 to the 8th, which is certainly greater than 400. So we can ignore plus or minus X. And so we can ignore that. So then we end up with X squared over 0.25 equals 5.6 times 10 to the negative 10th. Note, X in this case is the OH minus equilibrium concentration, not the H3O plus. That is a very common mistake students will make on this type of problem. They just assume that they take the negative log of X and that gives them their answer. They would be incorrect in this case. So we take our 5.6 times 10 to the negative 10th. We multiply it by 0.25. We take the square root of that. And we get unrounded 1.18322 times 10 to the negative 5th moles per liter. So if we take the negative log of that, which would give us the pOH, that would be 4.93 for the pOH. So remember, 2 sig figs here means 2 decimal places here. If we take 14 minus our pOH, that will give us our pH. And so 14 minus our answer from the previous is 9.07. Because our acetate ions, because they're the conjugate base of a weak acid, acetic acid, they're going to result in a basic solution rather than an acidic solution, as if we had put acetic acid in, if that were the major component. So this is an example of doing a KB problem. It's got a couple of other steps in it, things that you need to be careful about, okay? So remember that for conjugate acid-base pairs, we can convert between Ka and Kb by using 1.0 times 10 to the negative 14th. Also remember, on these types of problems, that if you're doing a KB problem, you're going to be, X will be the OH minus concentration. And the easiest way I've found to get pH from an OH minus concentration is to just subtract that value to the correct number of sig figs from 14 to get the pH value. So you subtract your pOH, negative log of your OH minus concentration, which again, for a KB problem, that's X. And then we subtract it from 14, we get our pH. Okay. So that is our full rundown of Ka and Kb equilibrium problems.